Okay. Hmm.
Scraping the wall is 100%.
All right.
Yeah.
Hey. Oh, I'm so excited. Thanks so much for doing this. It's just like,
My pleasure.
it makes learning so much more fun when I'm like, oh, I can like, it's cool. Yeah. Yes.
Is there any, like, other than that they're the same kind of graph, is there any relationship between what is the Australia one and what is the search party one?
No, so these are just some examples of graphs.
Mm-hmm.
What graphs are. So, hello, hypothetical video person. So yes, these are just some examples of graphs.
Mm-hmm.
So this is a graph of the railway between Australian capital cities.
True. Okay. Yeah. I've been on that one.
Oh, nice.
Oh. I just did that and then I had the compulsion to press the undo button because I've been doodling on my iPad so much. No undo button in real life.
One of the worst things about real life. This is people who have kissed each other in Search Party.
I was going to suggest that, but then I just thought it was so implausible that Drew and Elliot or Drew and Portia had kissed.
There's that one scene in season 4 when they all just do that weird three-way make out.
I don't think I remember that, which doesn't mean I haven't seen it. It just means that I've got a terrible memory, which I do.
Yeah, there's just like a weird, it's like when Dory's disappeared, when she's being abducted, and it's like this weird moment where they'll just kind of like, something's happening, they'll kind of get closer, and then they just like, oh my god. Like,
that's very funny. It seems very that show, but
yeah.
Yeah. Amazing.
Yes. So this is the people on there is just people who
wait, Dory and Dale kiss?
Yeah, there's like a thing. This is also something I forgot because I was like reading this today. Apparently, there's like Gail said something about like, yeah, like Dory's gonna be like, the other night I woke up and she was just kissing me or something. It's just like some weird offhand reference of like of that. So that's what that's from.
Yeah. Yeah. All
Yeah.
the others is pretty straightforward. Yeah.
And this is just a graph that doesn't have any labels.
Yeah. Cool.
So it could also be more specific. So this is a graph of Australia railway between Australian capital cities.
Mm-hmm.
The vertices are Australian capital cities.
Vertices. Okay.
And the edges are railway connections between cities.
Okay. So vertices are like the little.
Exactly. And here the vertices are people who kiss the main cast of Search Party, and the edges are people kisses between people.
Yeah.
Here the vertices are vertices, and the edges are edges.
Right.
Yes. So what the first task is just to come up with some other ideas of things that we could represent as graphs. There's obviously not, well, no, I hate when people say there's no right or wrong answers. There almost always are right or wrong answers, but there's a very wide range of correct answers, is what I mean by that. It's not like these couple of things I'm looking for, like there's almost anything you could put into this form. So just like come up with some fun possibilities.
First thought is that I could make a graph where the vertices are rooms of this house and the edges are direct doorways between.
Love that. Should we make that graph?
Yeah, let's do it.
Wow.
Hey, while I start this, do you want to see whether or not the curry has really well done? Oh, I don't need to rub anything out to do this. I can just do it. Okay. Is a hallway room. I'm gonna call it the hall. So. I think that's the graph.
Great. Oh, interesting. The whole is really central.
Yeah.
Great. Some other like things that we could do as graphs there and draw just options is like you could do a graph of like every page in Wikipedia and pages that link to each other. You could do a graph of every artist on Spotify and those who like collaborate with each other.
Yeah.
Yeah.
Cool.
Fun things. Cool. So now, I kind of told you what graphs are, but more in a like, here's some examples, here's a vague sense that I haven't really given a precise mathematical definition. So now your next task is is to, like, if you were like the kid in class who just wanted to like be really annoying, to like come up with like some examples of graphs that it's like very ambiguous whether they would count as a graph or not based on what we've said so far. Like it was like, well, what about this? Is this a graph? I'm trying to find annoying examples. I'll just let you.
Okay. And
so your aim is like it's like you want, like if the teacher just has this level of understanding, you want them to be like, is that a graph? Well, I don't know.
Yeah.
You know?
Okay. So a graph that's not a graph.
And again, this is like pretty open-ended because there's obviously lots of ways to ambiguous. Or you could think about it as things where you're just uncertain what would count as a graph.
What if I took this information and just expressed it as like so it's like the same information in the sense that like all of the edges are direct doorways between, but just that part. Like, is this a graph?
Cool. So this is you just like bring like the labels for the edges and then like not vertices.
Yeah. Well, because if the information you're trying to convey with this is like there are doors between things, then you could just be like door.
Right.
Is that not a graph?
Well, we'll find out soon. So I'll just let you do like a bunch of examples and then we'll go through and then that will lead us to a precise mathematical definition of what counts as a graph. Great. This is a great example. You can also do leave it up there because then we'll go through.
Okay, cool. I'll leave some of the doors.
Yeah, still the same idea. Yeah.
Put one more year and then just like that's the and then we're just gonna really.
And you can also do because mainly about the structure. So like this definitely could be a thing. And you also don't have to like label them like these. So you can just do things in terms of like lines and dots or whatever stuff. Yeah.
So like
great. It's a sad face. Is this a graph?
Is it sad?
You don't know. Nonplussed.
What about
wow.
My nipples graphs.
Okay, what else you got?
What if it's like there's some points and then that's an edge, but this edge goes
sneaky.
Why can't the edge go like that?
Yeah, why not?
Or that. Is that a graph?
Cool.
All edge. We'll call this one the edge lord.
Edge lord.
5,000.
Great.
More or is that enough?
I can try and get like two more.
Two more.
Yeah.
Okay.
Cool. Yeah.
And one more. Is it a graph? I feel like this is probably pretty uncontroversial, but like if that's like that and that's like that,
Is that two graphs? Can that be a
yeah,
graph?
is that two graphs? Yeah. Is there, if there's, so I feel like interestingly in direct doorway graph and in Australia graph, it seemed permissible to have like one isolated thing with no connection, with no, crucially with no connections between it and anything else. So it's sort of demonstrating that its relationship to the other things is that it's not connected. But if you can demonstrate that this thing has a relationship to something else, and meanwhile there's this whole other thing going on, are they two different sets that need to be in two different graphs?
Yeah, great. Okay, so before we reveal how mathematicians have chosen to define a graph, I guess like there's actually in a certain way even some ambiguity. So obviously like exactly how you define a graph is just like a choice, right? Like this is the thing we invented. So we could include all of those or none of those or whatever, depending on how we want to define it. And there's like one certain like reasonably restrictive way mathematicians have defined graphs, which is also known as like a simple graph. But then there's kind of like modifications or kind of more permissive definitions that let you do more things that sometimes, so like the simplest one, sometimes we'll refer to that as like a simple graph if you're trying to like distinguish it from the others, but also sometimes just like a graph, like it just says a graph and a simple graph. But then there's other things that are called things like multi-graphs or directed graphs or things we can talk about. So there's like, yeah, in a sense, there's not one single definition. There is like the default definition, but then there is also these like different versions that we can work with if we want to. So, but on the kind of simplest default definition, the simple graph definition, let's go through. So, yeah, cool. I was like, should I like tell you the definition and then you see what counts for? But I think it's probably better if I like go through what counts and then we can be like, what is this? Cool. So on the usual way, so this we've just got an edge and their vertices. We would not include that as a graph. The edge below. This we have a vertice and an edge. I love this edges. It's so cool.
Oh, I thought this was two vertices that were inside one another. Although a vertice and an edge is okay as well.
Well, because depending. So if it's a vertice and an edge, this wouldn't. Oh, and I was just gonna say like, yeah, so that would not be a graph because there's an edge that is not between two vertices. This would not, if that's an edge, it would not be a graph because again, there's an edge that is not between two vertices. If it's two vertices like on top of each other, it's kind of ambiguous. If you're just saying these are two vertices and I happen to draw them like one on top of the other, then that is a graph. If like you're specifically, if this is a way of specifically representing like the concept of a vertice being like inside another vertice, that's like not something that is like part of graph language. But if you're just like, I just wanted to draw like that, so like space, that's totally a graph. This again is not a graph because we have an edge that's not between two vertices. This, if we've just like chosen to draw that as a curve Zugoni, that's totally a graph. You don't like, yeah, when you're drawing it, you don't like the lines don't have to be in a particular shape or the dots or anything. Again, similar thing, we've got edges that aren't between two vertices, so it might be a graph. This is fine. You can draw vertices however you want. It's just like a way of representing it. This also is a graph. This can be a single graph, even though we have these two different components. And actually, in particular, this is a particular type of graph, which we would call a disconnected graph.
Cool.
Variants more specifically what it means. There's also like taxonomy graphs, which is that's this type of graph. That's this type of graph.
Yeah. All right. I reckon I could probably take a guess at the definition of a single graph in that case.
Yeah.
I reckon that to count as a simple graph, or like how mathematicians have chosen to define a simple graph, would be this is so wet. And the broccoli is getting overcooked. I'm mad about it. A simple graph would be you have to have one or more vertices, which presumably each vertice is like a data point, but I'm sure we'll get into that. And then to the extent that there are any edges that demonstrate the relationship between the vertices, the edges must always connect between two vertices, and all of the edges on the graph have to demonstrate the same relationship between the vertices.
Okay, great. So that's great. So I'll start from that and then be like, what are the modifications and how the mathematicians do it? So I guess the first thing is that like mathematicians don't really care in general, and also in this case, about like sort of content or what things are representing. So there's actually like nothing in the definition of graph about like things being data points or things representing relationships or anything like that. Like that is like something that we then use graphs for, but it's kind of separate to like the definition of graphs themselves. But yes, you were saying it's one or more vertices. So fun, great. So okay, basically the way we're defining it here, we're saying it's a tuple, which is like a pair of things. One of the things is a set, the set of vertices. You know about sets.
Yeah.
But it doesn't have to have one or more. It can be empty. So that is a graph.
Okay.
It's called the Null Graph.
Yeah. Cool.
The graph with no vertices and no edges.
Yeah.
So
horrifying.
Yeah. So we've got a set of vertices. It's a set. And then maybe that's not really complementation, but it's fine. And then we have a set of edges. And the way we define edges, like purely mathematically, without talking about how to represent relationships or stuff, is we just say that that is also a set, and it is a set of subsets of this set. So what that means, so a subset is like you take some certain elements that are in that set. So say the vertices is like these people, Portia, Elliot, girl, etc., like a subset of them is Portia and Elliot. A subset is also like Portia, Elliot, Drew, but these specifically have to be two element subsets. And so it's a set of two element subsets of this. So like in this case, it would have to be Gail Dory, Portia, Elliot. So like two dimensions to be efficient. Like this would be one of the subsets in this set of edges. And mathematically, and this could also be so have no edges. That's fine. That's a graph. And so mathematically, this is literally all we say. We don't say anything about it. So we're just like it's a set, and then another set of subsets of that set. And that's a graph.
And the
of two element subsets.
Two element subsets. Yeah. Infuriating. No, I love it. That's great. That's clear. It's very clear.
Yeah, and like we're totally separating the content from the form. And then
I've made a decision, and my decision is that although I would like this to be thicker, it's time to
I support this.
Yeah.
Sometimes you just gotta call it.
Yeah. I'll dish up for us and we'll keep going. You hungry? Very hungry? Not so hungry? Yeah. It's always good. You can always come back for more. You want to even just serve yourself, right? Rice over there, and then.
But also just, I don't know why, but for some reason it makes me so happy that that's empty. Like I think there are reasons that I probably just like with mathematical reasons that like things easy to work with and like you get everything you do, but also just like I'm purely like cheekiness level or something.
Yeah.
There's just nothing happens. Just two empty sets.
Yeah. Well, it also seems important in the sense that like one of the hardest things for me in learning these mathematical things is trying not to think about applications. Trying to just like, what do you mean by that? Actually,
I just kind of was here so I interpret that.
That's really actually
cool. I actually think it's usually pretty helpful to think about applications.
Yeah.
Like,
Okay.
the math is phrased in a different way, but I don't think that is the best way to understand it, right? Like, for example, like I find obviously traits do not start with that trait definition, right? We can go with examples and things, and then it's easy to go what that means.
Yeah.
And just look at like we just started off today, and I was like, all right, we're talking about graphs. The graphs is a pair of sets. The second is a set of two element subsets of the first stage.
I've been like, quite tired, so
yeah.
see ya.
Yeah, so I think it's really helpful to have applications in mind, while also being able to do the like, yeah, pure mathematical things.
Thank you, that's book.
What about a spoon? Oh. Yeah, and I think as we go into doing things, you kind of probably see more of the utility of this thing. Like, I think this type of stuff is good, like understanding concepts.
Yeah.
And if you're trying to do something like write a proof or something, it's something that becomes super, super useful to have just like a super precise thing. Because you do get these weird things where you're like, oh, this count, or like, what can I do with this? And it's like so nice to just be like, okay, it's just this pair of sets, and I know how sets work, etc.
Yeah.
Great. So that's how strict definition of a set. Any more terms to explain this? We know what vertices are.
Mm-hmm.
We know what edges are. Edges have vertices. And so this graphical thing is just like a way of like a convenient way of representing graphs.
Mm-hmm.
Right?
Okay.
We could also like by drawing it, but we could also represent it. Like we could say just write like everyone's names as a set, and then we could just write like all the pairs, Porsche, Elliot, Drew, Elliot, etc.
Mm-hmm.
That would be like another way of representing a graph.
Mm-hmm.
This is just obviously much more handy for human eyes.
Yeah, cool.
Yeah, so the graphic node with nothing in it is called the null graph.
Yeah.
And the graph with just one vertex, which is also pretty cute, is called the trivial graph. Mathematicians love to call things trivial.
Mm-hmm.
Yeah, there are like variations on types of graphs. So like things that aren't simple graphs is, for example, like in a multi-graph, you can do things like this. Like maybe you might have something where it's like the amount of time people have kissed or something as an edge.
Sure.
You have directed graphs, which have arrows.
Mm-hmm.
So say that you want to say like an org chart or something, you might want to be like this person supervises this person, etc. But there's like a direction to the relationship. It's not just like a connected.
Well, yeah, that's like when I was looking at this one, I was like, a lot of the hypotheses I had about what it might be a graph of, I was like, oh, I don't think it can be a graph of that, because I think you would need to, to fairly represent that, you would have to demonstrate like a directional relationship.
Yeah, exactly. So these are like other nice types of graphs. Cool. So new concept we're going to do something with, which is called the degree of a vertex. So the degree of the Porsche vertex is 2. The degree of the Gale vertex is 1. The degree of the Dory vertex is 4. Probably, yeah, getting it right.
Number of edges that connect to that vertex.
Exactly, yes. And the terminology we use for connect to the vertex is the number of edges incident. Hang on. The number of edges that the vertex is incident on. But a more fun way to talk about it, actually, this is, yeah, the number of edges that the vertex is incident on is the degree. We also, if we're talking about all the vertices that it connects to, that's called the neighborhood of the vertex.
So one into like multiple vertices, one vertex?
Exactly, yeah. So the neighborhood of Dory is Julian, Keith, Gale, and Drew. And you say vertices and neighbors.
Yeah, great.
So we have like some proofing thing like show that all neighbors are with us. Great, that's a degree. Cool. The first more kind of like meaty task, and definitely is yeah, you definitely don't have to just like sit there and like think about it and be like, I've got the answer to this thing. You can kind of like work through it. But it is about, can we, so we have some graph, but we don't know about the degrees. Maybe let's say like, you know, we know like how many vertices there are. We don't know anything about the edges. Like there are edges, we don't know anything. We don't know about the connections. Like, we know these people, we don't know who's two or something. Is there anything we can say without like knowing any specific information about the degree of vertices in here? So say if I just like pick one random, is there anything I can say to put like an upper or a lower bound saying, well, the degree is going to be like at least this, or it's like not going to be more than this.
Yeah.
Just from this.
Well, I suppose like, so long as it's not a multi-graph, we would say that the range, the possible range for the degree of the vertex is between 0 to 5.
Right. I agree. And if we wanted to generalize that for all graphs, not just 5-element graphs, how might we state that as just like a general rule that holds for all graphs?
That the degree of any given vertex is in the range of 0 to the cardinality of the set minus 1.
Right. And I'll compare the notation of that. Well, the cardinality of the set is, well, what we call that is the order of the graph. That's just the number of vertices. So the order of this is 5, the order of this is.
Wait, hang on. Is that the number?
Oh, sorry,
order of
order of
vertices?
vertices. Yeah.
So order of the graph is just the number of vertices.
Yeah, exactly. And notation for that is, so say if this graph is called G, then the notation, I think that is usually some way to do it. Yeah. So the notation for the set of vertices is this. That just means the vertices of G. So for example, for this, it would be the set of people, just this thing here. And then we can say the cardinality of that set. So for what you just said, yeah, you're saying that it's the cardinality of the set minus 1, and the degree of every vertex is less than or equal to that.
Oh, great. Yeah.
Cool.
How did you notate vertex?
Yeah,
Is
so
that a little b?
Degree, I just did a little b. Yeah, that's kind of, you can use different letters. That's not like this is like an actual notation convention. What you use for it are, what you use for it is kind of a convention that you use v, but it's like a weak convention or something. Like it's more just like a handy, whereas this is like, that's actually what that means.
Yeah. Are the lines either side of VG, is that the notation for cardinality?
Exactly.
Yeah, cool.
Yeah. Great. So this is our first result in graph theory. Just derived your first result of our graphs. So
Cool.
Congratulations.
Yeah. I can't believe how recently I learned about the cardinality of sets.
Yeah, just all over it.
Wow.
Great. So there's our first result. Let's I'll leave it at that. Maybe we can quick, review theorem by the end of the night. This is going at the speed this is going. Yeah. Cool. So can we put any upper or lower bound on the total number of edges in a graph?
Oh, wow. Fuck. Yeah. So it'll be a similar thing of like less than or equal to, because you don't really need to define the lower limit because it can be 0, 0. And then I don't know I can't remember what this is called, but yeah, I can. Okay, hang on. I can,
go for it.
I don't know what this is called, but I'm gonna do a small number so that I survive. So you do like whatever calculation you do to go like that plus that plus that. Like how you figure out what's that called?
The what?
Like, okay. If you have like, because okay, I'll tell you what this is. I'll give you the example.
Yeah.
That I was thinking of the other day. I think this is relevant to graph theory, and I think it's relevant to your question. So we need this. I saw a movie poster the other day, and it had on it 3 male actors and 2 female actors, and then up here it had like the names of 2 headliners, and they were both men. And I was like, oh, like really? There are 2 women on the poster and neither of them get a name, but 2 boys get a name? That's so bad. And then I was like, what's the probability if it was just if they randomly chose 2 actors' names to put at the top out of the 5, what's the probability of it being 2 men? Yeah. And I was able to figure out that it's like probability of 3 in 10. It's a 3 in 10 chance that they get 2 men's names. It's only a 1 in 10 chance they get 2 women's names. but it's a 6 in 10 chance that they get like a man and a woman.
Cool.
So, and I just figured that out by going like, okay, so I'll color in the men in this right? And because I don't know how to do the maths, what I'm going to call digitally, I'm just manually went like, okay, man, woman, man, woman, man, woman, man, woman.
It's a star.
And it's a star.
Right, so you found every possible combination of actors.
Yeah, but I specifically did it by like their faces are arranged literally in this pattern. Yeah. And I was just stopped at a red light for ages, and I literally did it by like drawing lines like this with my brain. But there's a mathematical way of doing that that I don't know how to do, and I also don't know what it's called.
Yeah, cool. I can definitely explain that.
But that's how you would find the number of possible edges.
Yes. So what?
I know it's the longest way of explaining you.
No,
the number of edges by drawing them.
No, that's great, because the principle is that you're looking at every possible combination, right?
Yeah.
Great. So let's think about like how we would do this mathematically. How might you start thinking about that if you were like, how would I find this mathematically? So you kind of like break it, maybe like a good way. Well, one generally good thing that you already did, though you seem to be almost like excusing the fact that you're doing it, is like choosing like a specific, really simple example. When you're like, I'm just going to draw a simple graph. That's like a very useful and very respectable mathematical thing to do. If you're trying to like work out some very general thing, you're like, I'm going to choose the simplest possible example, and I'm going to like work with that, and then I'll understand the problem. So great instincts there. Also, I don't remember what the other thing I was going to say was. Breaking it down into parts. So like working out this thing is like sort of complicated. Everything like you could start by being like, okay, like how can I kind of break this problem down into parts? Like what are like the various things that I want to do, even if I have to kind of like put question marks over part of that. I'm like, I don't know how to do that. Like I want to work out this and then this, and then I'll combine them in this way or something. How might you start breaking it down?
Do you find the number by getting the total number, like to get the maximum number of edges in a set, you get the total number of vertices, and then you add like, it's like if the total number is 5, you find out the total possible number of edges by adding like 4 plus 3 plus 2 plus 1. That's how that works? So you just like find the number, and then like the next lowest number, you just add that to the next lowest number until you're at 1.
Yeah, great. So let's just this. So if we've got that 5, so we'll get to the first one. What did you say we start with? What number do we start with? So
in that 5.
5.
In that case, you start with 4.
Yeah. 4, and the next one we just had 3. For the next one we just had 2, and for that we had 1, and we have the right.
Yeah.
And so what do we get if we add 5 plus 4 plus 3?
Oh, I don't think you had 5. I think you
sorry,
had 4 plus 3 plus 1.
Is 7, 9, which is 10.
Yeah. Which is correct.
And that is correct. So, hang on. What's happening here? Oh, yes, great. Cool. So, how do you write that in, like, in a general way, not just for the, for the specific graph? This is great to like start with a specific thing and then be like, how do we generalize this?
So I have an idea for how to express it, and I reckon that there'll be like a mathematical notation way of like making it more simple. But if you go like the cardinality of the set minus 1, plus.
I'll let you write actually.
Okay. I'm gonna need a pretty broad, expansive whiteboard, I think, for this. I'll start here and I might need to type some stuff up now. So I have to put brackets around this.
Yeah, totally.
is there a way where I could go x equals
How the efficiency. Totally.
and then the thing that we're looking for is x. Hang on. No, that's not what I want either. What I'm trying to find, I know not to express it as -1 plus x minus 2 plus x minus 3, because that doesn't register when you hit the limit of like there's only one connection.
Well, you actually could. A fine thing to do in math notation is just to do this. Very acceptable.
But the thing is,
I mean,
that I'm not
not
doing plus
ones.
ones. I'm not doing plus ones, I'm doing minus. Like, but what's the plus 1 part?
But we do it until we get down to 1.
But I'm not doing 4 plus 3 plus 2 plus 1. Because it would be. Oh, are you saying that this notation just means do this until x minus
Something
4
like that.
equals 1?
Yeah.
Really?
Yes. Yeah, I'm pretty sure that would be fine. Because we know what you mean, right? As long as mathematics is like in a weird way, there's like plus stuff that you would think. It's like if it's like it has to be clear what you mean. But if it's like clear, but so we could write there like I also always would write this, but I mean you could if you wanted to be like pedantic, you could just do like x, right? Like that just keep going up until it gets to x, which is 0, and then
But how is x 0 though?
I just like x minus x is 0. Like this is
Ah,
going like we're going. It's a similar idea. We're just going 1, 2, 3 until we get up to x. That's basically the same. It's just like minus until we get down to 1. But yeah, these are both ways we represent it. Great.
and it seems so counterintuitive to me. Like I don't know how you could read that and understand that the increasing numbers that go -1, -2, -3 stop at the point where like
Where it
x
becomes
minus
Yeah.
whatever the number is equal to 1.
Yeah, interesting. I guess I'm just like so used to it that it like seems intuitive, but I guess it's like not if you like haven't seen it. Yeah.
No.
Great. And this is the maximum number of edges. Now, is there a way? So we can imagine, say we know a graph has like 3,000 vertices or something. And now we want to calculate this. Obviously, if we have it like this, that's going to like take a long time to calculate, right? We've got to add up 3,000 to
Yeah.
Now, the question is there like a simpler way to represent this that we can put into a calculator in like way less time?
I mean, surely.
And maybe I'll just help you, but maybe I'll go first. Like, is there a way that you can use our first derived result? We do call these things. Let's call this like lemma 1. Lemma is just like when something is a theorem. A theorem is just like a mathematical statement that has been proved. And then a lemma is like technically it's like a little subpart of that theorem. So say you're trying to prove something, and like along the way you're like, oh, well, I have to like show that this is the case and this is the case, and in case I don't use them, we call them like lemmas, so like something to be proved. But then also there's just like a weird thing where like if something happened to be first proved as like a lemma, even if then people just use that as independent result, it's like, oh, I've called a lemma, just like a little mini proof. So let's just call this a lemma because that's fun. Technically, we haven't actually proved it. Let's call that out like lemma 1 maybe. Is there a way that you can use this result? If you think about this in a slightly different way, can we use this to? I mean, I guess I'm saying we can use this to think about this question of the maximum number of edges in a slightly different way, which will, might give us a form which is easy to calculate. So we're talking about, so this is telling us what the degrees are less than or equal to, and now we're thinking about like maximums, right? So we're just interested in the.
So the cardinality of the set -1 Yeah, I actually can't think of a simpler way to express it.
When in
Like, I
doubt,
know that there will be, but I can't think of one.
I can totally tell you, but also when in doubt, always just start drawing or writing something on the whiteboard. This is another weird little work math break. You're like, I don't know, I don't even know where I start. And then like sometimes if you just start writing things, you're like, oh.
All right.
Or like, you know, drawing some examples or yeah.
So brain, don't fail me now. Is it like okay. I'm gonna write something I know is wrong, but
Cool.
which I hope will take us in the right direction.
Great.
So I know it isn't this.
Yeah, it is not that, and it is also a great starting point.
Yeah.
Yeah.
Okay.
No, yeah, a word counts. Yeah.
Um.
And
I
why do you
feel-
know it's not that?
Well, I only know it's not that because I tested it in my head with 5 times 4, and I was
Yeah.
like, that's double.
Yeah.
That's actually double in that case.
Why might it be double in that case?
Okay. Yeah, fine. Because, well, this ended up being 5 times 2 ended up being the that. No, the that. But it's not always going to be times 2, obviously. But it is always going to be times something.
Why don't you try a even simpler example?
So the number of those is 3. And then number of connections ends up being 3. Less than or equals 3. Hang on, no, that would be less than or equal to 2 because it's 3 minus 1. But the total number of possible edges is 3. And the number of vertices is also 3. Okay. So.
And what do you get for this formula in this case?
In this,
Yeah.
Go, 6. So that this formula always ends up being, no, not always, we can't say always, but in both of those cases, it ended up being double the desired result.
Yes. So we don't have a proof that it's always double, but we have a suggestion of a possibility that we might want to investigate.
Yeah.
Which often happens.
Oh, is it just? No, it's not that.
So in these 2 cases, it is that because it has been 2. But so you've noticed this pattern twice. It's probably helpful to think to be like, okay, can I think of any reason why this would be a consistent pattern and not just coincidence or just coincidence? Like, can I think of any, if you think about like where this came from, like how you derived this thing, can you think of any like general reason why it might end up being twice the number?
I can think of a reason why it would in general end up being more than the correct answer.
Yeah.
I can't think of any reason why that would be exactly double.
Yeah, what's that reason?
Because in that example we had before with n equals 5, it went 4 plus 3 plus 2 plus 1. And so you ended up dividing, this was 5, multiplying 5 by 4, which is the largest number in this set. And it looks like you'd actually be looking for the average number in this set.
We're looking for the total, right?
Oh, but in terms of how you would express this as a formula.
Oh, gotcha. I was even thinking like, even if we forget that plus thing and just think about like the meaning of these things in terms of that, yeah. Actually, I reckon I will explain, I'll explain this thing to you and then we can do another thing. Is that all right if I just like tell you? Oh,
yeah. Can I quickly do a thing?
Yeah.
I don't think this is right either, but I had it as this times this minus 1, but is that correct?
Well, that won't be correct even in these examples, right? Because the thing you had before divided by 2 was correct for these examples.
Was that correct for these 2 examples?
Well, you got twice the amount, right? So it means if you divide it by 2.
But I'm only putting half of the equation over 2. I'm not putting the whole equation.
Ah, cool. So that's the same thing, just algebraically.
Is it?
If you got multiplications, because what's the simplest way to explain that? If you so think about it like this, like if you double something, if you think of like multiplication as like creating some number of copies of something, and you think of like division as like dividing that between different people, dividing it out. Like if you have some amount of a thing and you like double it and then split that between 3 people, or if you like have some amount of thing and you split that between 3 people and then double it. Hang on. Okay, maybe I won't try to explain that now. Maybe I'll just say that is a rule that if you have like a series of multiplications, then like dividing it all or just one of them or 2 of them, whatever, it's like all the same as long as like that division is happening.
I don't understand that on this for this reason though.
Yeah.
Because when it was 5 times 4,
yeah.
If you did 5 over 2 times 4 over 2, 5 over 2 is 2.5 and 4 over 2 is 2, and that equals 5. But if you say it's 5 times 4 over 2, that's 5 times 2, which is 10.
Exactly. So great. So this is different to just having it all over 2. Because you're dividing it twice versus once. So when you do this, you're dividing it twice. There's 2 divisions. But if you just have that, it's only 1 division. Or if you have it all over 2, that's only 1 division. So the important thing is that like somewhere along that you're dividing it by 2 once.
Oh, okay. So if I expressed it as, I've got a feeling that I'm still not understanding this, but if I express this as like that over 2 and this over 1, is that's
the same, yeah.
That's the same as just having the whole thing over 2.
Exactly.
But I don't get it, because this in the graph we were using, like the cardinality of the set was 5. And when this was -1, that number was 4.
Yeah.
If I say I want to do like cardinality of the set times cardinality of the set -1 over 2, I would be effectively saying I want to do 5 times 2.
Yeah.
But if the thing you're saying of like if this is over 2, then it's all over 2, then that becomes 2.5 times 2.
So that's different because there you're dividing it by 2 twice. So that's different.
Oh, but
so the things that are the same is if you is this. But not
because so you're timing 5 times 4 first. It's an order of operation thing where you have to multiply both of those before you can do that.
So if you multiply it and then divide it all by 2,
okay,
that's the same as if you just divide one of them by 2 and then you multiply it.
Wait,
like
no,
if you split something in half,
okay,
and then you make 5 copies of it. That's the same as if you.
But so this where this is over 1 and this is over 2, where we retain the -1. This still in that case will be 5 times 2.
Yeah.
Okay, great. I just need to put over 1 here.
Over 1, yeah. Whenever you write something over 1, dividing something by 1 doesn't do anything. So,
yeah. So if I want to only divide that, if I want to divide only half of it by 2, only this part by 2, then I have to express that this is divided by 1.
No, you can also just write that. That's fine.
But didn't you say that equals 5 times 4 all over 2, which is a different result than 5 over 1 times 4/2.
So 5 times 4/2 is 5 times 2, which is 10, and 5 times 4/2 is 20 divided by 2, which is 10.
No, it didn't. Why isn't this making sense? Hang on, I feel like in order to like, I feel like maybe this is like much simpler. Hang on, are we getting caught? I want to understand this, but I don't think it's actually advancing.
Yeah, let's
the thing that you're
table
trying to-
this for the end.
Yeah, cool.
Yeah, I'm gonna write a little note multiplication.
Absolutely
So-
love that I'm trying to understand this like extremely intense graph theory, and I'm like, but wait, how do you?
It's so good. How do you multiply?
The other day I was on the, I was doing voiceover and we were doing it remotely because our actor was in Austria, and I was trying to figure out like how many pages we had to get through per hour in order to be making good time. And so I was trying to like direct the actor, and I also had to like read in the lines that like to play the scene with him. But then in a tab I had to open like how do you do long division? So good. I was like trying to like sort of
Wait, as
upon
opposed to
reflection.
typing into a calculator?
Literally live on the flight, I realized that I could have just typed like with the mental energy that it was saying, you know, like research long division. It would have been so much more efficient to just be like, what is 720 divided by whatever.
So the more relevant way you can write this, which also is a different way of like thinking about it. So we're writing the result, figure out differently. We're using this first result. So if we take this example, we know that the maximum degree for each of these vertices is call it n. Yeah, the order times, sorry, the order minus 1. Right?
Yeah, that's the maximum.
So if we add that out, which is what you're doing, right? So we're like the maximum for this, maximum for this, maximum for this, maximum for this. And then we get n times n minus 1. Here's the kicker. Why would that, what? Is there any reason that would be double? Well, let's look at this edge by edge. So this edge here,
Make this
oh, true. This edge here is incident on this vertex is incident on the edge.
Oh, is it counting as a new edge every like directional version of the edge? Like that to that is being counted as one edge, and that to that is also being counted as one edge.
Exactly, because we're counting the degree, that's right. So we're counting this 4, and then we're going 1, 2, 3, 4, 1, 2, 3, 4. But look, like that edge is now going to count twice.
Yeah,
it's going to happen to every single edge. So we're counting every edge twice.
Yeah, we don't want that.
So now to do that, I'll just divide it by 2, and that is the maximum.
Yay! I was so close.
Yeah, totally. And there's so much more friendly.
Oh, amazing. Yeah, because you're basically saying there's no simplified way of counting every edge, but there's a simplified way of double counting every edge, and then we just cut that in half.
Exactly.
Amazing.
Yeah, so that's our second result. Write that one down.
So
Double that. What should we name that?
what should we name
Summit
it?
theorem. Yeah. Probably has a name.
What's something that gets double counted?
No.
The branch stacking theorem.
Great. That sounds very modern. The branch stacking theorem. Cool. So that's our second result.
Yay!
Yay.
Exciting.
Yeah. This will be something we'll need to use and work out on the thing. So I would write this one down.
Oh, yeah.
All right. This is the real shit now. Terms. Oh yes, I explained the term order. Oh, sorry, just look at that.
You know what's going to really get me over time? I'm so used to thinking of the word vertice as relating to lines.
To lines. Oh.
Calculate maximum edges.
Not vector.
No, vertice.
Oh.
Because aren't the vertices of like a 3D prism the edges of it?
No, they're the vertices on it.
Fuck, that's funny. That's fucking rules. I like that. That was really good.
I didn't even know what came out. I was like, they're the dots between, they're the corners. Yeah.
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 You can say that again. Fuck. Well, maybe it's because even though they are the same thing, I'm used to thinking of them in the context of fucking whatever, who cares? The reason this will be hard for me to integrate is because I've been wrong.
Isn't that, I think that covers like 60% of all human experience.
Yeah.
Great, so you've got the map edges, cool. And the word we use for a graph which has a maximum of edges like this is a complete graph. I think it's quite nice. So for example, if we did a graph of the cast of Friends,
Yeah,
and who knew each other, it would be a complete graph.
Yeah. The main cast of Friends.
The main cast of Friends, yes, the 6 friends. If only like none of them like related and stuff, you could be like the graph of who's friends in Friends is a complete graph, but like, you know, Chandler and Monica are
It's content.
brother and sister, so is that right? Yeah.
Chandler and Monica are married.
Ross and Monica. Who's
Oh yeah, Ross and Monica.
Ross and Monica. Cool.
Yeah, I was like, they're on.
They really ruined it. Great, it's a complete graph. Okay.
That's so fucking funny. That the list of people who are friends in Friends is not a complete graph.
Yeah. There's like one missing edge.
Yeah. They should call it friendship group. That makes room for some of the
they're not
people
all
like
friends, yeah.
not big friends.
Or maybe it's just they're like, well, it's not about it. I did stumble across when I was like, I was going to do one of Friends, and I was like trying to look up friend things for graph theory, and someone had done like this whole analysis of like who has storylines together. I was like, who is like in storylines together the most, and also like who has their own storylines the most, who just like has no storylines and stuff. And that was interesting, being like, who's not prioritized. Anyway, okay, something a bit more tricky. If we know the degrees, how do I approach this? Yeah, okay, cool. This is a fun one. Well, I think it's fun. Okay, so we've done where we know how many vertices there are, and we can work out the maximum degree of any vertice.
Yeah.
We've done that we know how many vertices there are, we can work out the maximum total amount of edges. What if we know if we know the degrees of all the vertices, can we work out how many edges there are, or can we not?
Yeah. When you say we know the degrees of all the vertices, we know those numbers individually, or we know the sum total of the degrees of the vertices?
Would you like to?
Oh, well, I guess it's just ultimately like the total sum total of all degrees of vertices over 2. Right? Yeah.
Great.
But I'm sure there's a clever letter for that.
Yeah, there's ways we can, but this is right. So I'll show you like a short way to write it, but it's important to the like this is correct. It's just like a handy way to write it.
Yeah.
And writing things also, like one thing I found surprising studying math is like you actually encourage like more to write things out, which is symbols.
Yeah.
Like it's common that you're like writing all this math and like, why don't you just write that in a sentence?
Yeah. Yeah.
So
Cool.
writing things is fine. It's more, when there's things that maybe get like longer but awkward and you're like, it's a simple symbol, but like writing words and saying like, this has to be the case of this other guy is like totally fine. As long as like, it's like is rigorous and like, it's not like becoming vague because of being in words. It's fine to use words. Yeah.
Cool.
Great. So the shorter way to write this is we could say, so this means the sum. I'll explain a bit more like how it means the sum. Degrees of vertices. So divided by 2. So this summing thing is what that just means is so this is V and VG means like for each of the vertices in the vertex set, we add them all up.
Yeah.
We add up the degree of that vertex.
Yeah.
Yeah. So just like take the first one, add the degree of that one, then take the next one, add the degree of that, and we'll add them all up.
Yeah.
So it's like you can do it like if you want it to be like yeah, I don't want to get into that. Yes. Great. So this is known as the Handshaking Theorem.
Oh,
because all the vertices shake
hands.
hands. It's usually written. This is totally equivalent. I actually don't know if there's even any reason this would be a better way to write it, but like usually people just write it in a slightly different form. Put the 2 side. So you go like the number, the sum of vertex degrees is twice the number of edges.
Okay.
But it's like totally the same concept, just a slightly different way of thinking about it. And
Yeah.
I don't think it is even necessary in modern school.
Yeah.
Yes, great. Okay, that was really good. But so that seems right. I don't know.
It's got a vibe.
Can we prove it?
I don't know how.
Let's find out. Well, that's what you're about to learn.
The idea of proving things is so scary because it sort of feels like you can prove it in any given instance or any chosen equation, but then you could just be missing the equation where it doesn't hold.
Exactly.
That's
That
so
is
scary.
so. Yeah. So how do you? So say when we went through, we had this before, like we went through. Oh, just on my computer.
Oh yeah.
I have all these timers where it like shuts down, or like locks me out of things and stuff. It's always fun when it go off. But yeah, so this like locked me out of my computer from like overnight.
I will say, I'm happy to keep going in the short term. My cognition is slowly fading, as evidenced by that time that I just like fully couldn't compute like basic division. And also Josiah will get home from a fairly long rehearsal at some point, and we might want to wrap up shortly after that.
That's it.
So that he can like be winding down, etc.
Yeah, should we say wrap up when Josiah tonight?
Yeah, I reckon wrap up. I think wrap up when Josiah arrives home, or 10:45, whichever occurs first.
Yes.
Yeah.
What if Josiah just decided to go for a 5-hour walk, and then we would be committed to going until 3 AM or something?
Yeah.
We didn't have that caveat.
Yeah.
Cool. Okay, so yes. So like because before you have it, you're like, well, in this case it's divided by 2 for the total, in this case it's divided times 2 or whatever, will hold for everything. So we need to prove things that write a list of 2 hold for everything. So we can't just write a list of examples and be like, it's true for these, right? Like,
yeah.
Which also is just the case in general, right? You're trying to show things like if you're trying to be like, if someone's trying to be like, you know, make some argument like, oh, like no women can do math. They can just be like, this woman can't do math and this woman can't do math. So no woman can do math. Like we know that's clearly a bad argument.
Yeah.
And most of the rules for like, I guess more principles than rules, but for like how to do proofs are like very just analogous to like what intuitively makes sense as like a sound way to argue for something. Okay, so this seems right to us. How can we prove it? So I'm actually just going to ask you to prove it. I'm assuming that you are probably that can prove things before. But we're going to have a go, and then we will like see what we have there, and then we'll like make some modifications, like writing a first draft. Yeah. So prove this is the case.
Oh wow. So and I can't like the way to do this is not by being like, well, in this specific instance, it's what you just said. Like I can't just give specific instances in which it is true. There has to be some other way to prove that it's generalizably true.
Yes.
I don't even know it again.
So if you were just trying to, if you weren't thinking of it in terms of like, oh, I have to learn how to do a math proof because you think I know how to do, if you were just trying to convince me that it was true, how would you do that?
I would say
if I just came in and you're like, oh, I work as an and I was like, oh, really? What would you say?
Okay, I promise this isn't me using a specific example. This is just me having a visual aid.
Sure. And again, you can write like in words. It doesn't have to look super mathy.
I'm probably just going to say it out loud.
Yeah, great. That's a good quick one.
So we're trying to prove that the sum total of the degrees of the vertices over 2 is equal to the cardinality of the set of edges.
Yeah, or the number of edges would be a simple way to say it.
Yeah, the number of edges. Great. I just like saying cardinality because I know what it means now.
Just start saying that with everything, like instead of being like, just like how many like broccolis do we have? Like, just like what is the cardinality of a set of broccolis currently? Yes. I've just looked in and I'm like, is it? How do you think of that?
Yeah. Okay. So the reason that this is true is because any given edge definitionally must, oh, hang on, I'm going to use the right word. I wrote it down. Each vertice. No, I don't have the words for the edges. What's the opposite?
On?
So that's that the vertices are incident on edges, but are the edges incident?
The edges are incident on vertices. Yeah, not the other way around.
Okay, so any given edge must necessarily be incident on exactly 2 vertices. That is the definition of an edge. The degree of any given vertice is how many edges connect to that vertice. If we take so one source of information about the total number of edges in a graph is the sum total of the degree of the vertices. Because if we take each known vertice in the graph and we count how many edges connect to that vertice, we can't say edges are incident on that vertice. Or
edges are incident.
Yeah. If we sum all of those numbers, we have information about what seems to be the maximum total number of edges. However, any given edge has to connect to another. So then that's why we are dividing by 2, is because we will necessarily have double counted every edge.
Cool. Yeah, so that is like a definite like first draft of a proof. Like the form of paper said that. Okay, great. It's like finally it's like proof, like you. Cool. Yeah.
Great. Did I miss any logical steps? Like before.
What do you think was like the weakest or sketchiest part of that?
I think the weakest part is where I said something along the lines of like, once you sum all the degree of all the vertices, you have like some information about the edges.
I would agree. Like if someone said, what do you mean? Like, no, you don't. What would you say? How would you show what you mean and why it's true?
Once you sum the degree of all the degree of each vertice altogether from the graph, you have the total number of places where an edge is incident upon a vertice. We know that every edge is necessarily incident upon 2 vertices. So once you've found the number of places where an edge is incident upon a vertice, that's why you divide it by 2, is because we know that an edge by definition is always incident upon 2 vertices. Yeah,
I think that's a pretty solid proof.
Cool.
Like you know, it's like tied up in certain things, blah, 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 but like as a structure, that's like a pretty good proof. Yeah, I'll show you like, yeah, maybe how I would like do that in like a more tidy up way. But it like, yeah, that's what you said. Cool.
Yeah. Yay. Fun.
So we can now pull that. Now we can really pull that. So the way we can do that a bit more precisely is to be like, we can define a set. We can call it A, just to pause on it, and we can say that this is the set. This is like basically what you were saying. That it's like the set of vertice edge combinations where E is an edge, B is a vertice. Sorry, we should just intend to make sure we say that they're actually in. Obviously, like B is in the set of G and E is in the vertex of G. Yeah, E is in the edge set of G. And we're saying, and E is incident on B. What you were saying?
Yeah.
Right. So we're just saying it's every like combo. So it's like this and that, this and that, this and that, every combo. And then we can count this like in two ways. So the first way we can count it is we can say, well, every edge is going to be incident on two vertices. So for every edge, we're going to have, and just imagine that I'm writing these words, that can't be bothered. So for every edge, we're going to have two of these pairs. So therefore, the total number of pairs is going to be 2 times the number of edges. So the cardinality of A is that. And then if you look into the vertices, we're going to say, well, for every...
Wait, hang on. I think I got lost. What is A?
A is just this set of vertice edge pairs.
Yeah.
Cool.
Oh, gotcha.
Yeah.
So and then so A.
So
cardinality of A is
2.
2.
Is 2 times the number of edges.
Yeah.
So you can kind of think of it as like each of these points. So the way to think about it.
Yes. Okay. Good. Cool.
But we're like, just being a bit more specific what we mean there, we're like, well, that's there's like a pair of vertices and edge. The A for everyone where the edge is incident on that vertice. And we know that the size of that is 2 times the number of edges. And we also know that, so that's like we sort of kind of count from it by the edges. If you want to count their vertices, we know that every vertice, for each vertice, how many of these pairs will there be? Well, it depends on the degree of the vertex, right? So actually we can be a bit more explicit. So we can say like, it's the sum, rewriting in terms of edges, the sum over the edges is the way we would say it. So we go for each edge, and it's just 2, right? Each edge we just have 2 and we get the total, which is just 2 times the number of edges. And then another way to count it in terms of summing over the vertices, we can say, well, for each vertice, how many of these are there per vertice? Well, it's the degree of that particular vertice, right? Because how we define the degree of the vertice, which is how many edges are incident on it. And so this is going to be the number of edges times, sorry, this is going to be, this is just going to be that, that's that. And so then A equals both of these, then they have to equal each other, and that's a different.
Great.
Yeah.
Amazing.
Cool. Like the same structure.
Yeah. Cool. Yeah, makes sense.
And now, and then the theorem, and then we're like, cool, we know this, we don't have to worry if we just didn't, and look at a couple of examples or something, because these things all have to be true for every graph.
Great.
Handshake theorem.
Yeah. New theorem just dropped.
Yes. Did you write that one down already?
I didn't know.
Okay.
Do you
Sorry.
mind if I briefly check my phone?
No, go for it. Yeah.
See if. Or. Which is that on my right hand?
Cool. Yeah, as long as you have the result down, that's fine. So I reckon I'm going to prove one with you, and then obviously if you are able, I'll prove one thing and then give you like a problem to try.
Okay.
So
do you want any water or anything else?
oh yes, that would be good. Water.
Oh, you say you same glass?
Cool. So the only reason I'm proving this rather than going through it with you is so that in that time for you to do a problem. But now you know, now you understand proving things. So
Yeah.
So what I'm going to try to prove to you, I'm going to tell you the conclusion first because it might seem hard to prove false. Every graph, so let's define two things. So an odd vertice is just a vertice whose degree is odd. Okay. Right?
Yeah.
And an even vertice is a vertice whose degree is even.
Yeah.
Every graph has an even number of odd vertices. That's what I'm going to try and prove.
That's wild.
Every graph, including, all those graphs we can include, like we can do this weird graph, we can do like this thing that's different parts, whatever. They're all going to have an even number of odd vertices. Let's see if we can prove this.
Great. Even just a second's thought makes it. It's very common sense.
You prove it.
Because if an edge is necessarily incident upon exactly two vertices, then there would be no way for it just makes sense.
It doesn't. This is why we try to prove things, because then we see how wrong we are. I think this is the main effect. I've been reading this like full sort of philosophy of math proof book at the moment. And what it's like, proofs don't even that good for like being certain about things. They just like show you how wrong you were in the thing that made a lot of sense in your head when you try it. Yeah. So like every edge has to be inserted on two vertices.
Yep. And therefore any vertice, any odd vertice.
So let's say this is an odd vertice. It's got some odd number of things coming out.
Yeah.
Why can't there be like a bunch of even vertices and then two of them are odd?
Because that's an even number.
Sorry. Why can't this just be surrounded by all these vertices which all are even, like they connect to each other and stuff, and it just happens that like an odd number is connecting to that?
Always an even number because it would be an odd number if you have just one.
Like say we have three vertices and we've got all these other ones. They're all connecting different ways. And it just so happens that maybe like there's three connecting to that and one connecting to that and five connecting to that. And there's an odd number of odd vertices. I will anticlimactically tell you the answer. So the first thing we're going to use is that the total, so the sum of vertex degrees has to be even. This is like a simpler thing, more intuitive, because every edge, we know the sum of the vertex degrees. We can use a handshake theorem. Yeah. There's like a funny thing to do. You prove one thing and then you're like, oh, now I can use that to show the other thing. Yeah. And you kind of build up. So we know that the sum of the vertex degree, the sum of the edge, we know that the sum of the vertex degrees is twice the number of edges. This has to be an even number because it's 2 times something. Yeah. So we know the total is that. Okay. Now let's just consider, and we know all the vertices are either even or odd. That's all they can be. Yeah. If we look at just the even vertices, then if we just do the sum of the degree of the even vertices, we know that has to give us an even number, right? Yeah. Because we're timesing an even.
Because you've got like if hang on.
Oh, because it's even, because we're saying these vertices are all even.
Yeah.
And there's an even number of them.
Yeah.
So therefore the total has to be even.
Well, even if there's an odd number of even vertices, the total has to be even because you can't multiply a set of even numbers and arrive at one number. Yeah.
Okay, so that's even.
Yeah.
Now say we have an odd number of odd vertices.
Yeah.
That would give us an odd number of degrees from that. And even plus odd is odd.
Yeah.
So we'd have an odd total, but we
Yeah.
can't have that.
Mm-hmm.
So therefore, the odd total has to be even.
Mm-hmm.
And you can only get that if there's an even number of odd vertices.
Yeah.
So therefore, there's always an even number of odd vertices.
Unreal. Yeah. Makes sense. Yeah.
Cool.
Yeah.
Crazy.
Is it time for me to do a proof?
Of that?
A
No
problem.
problem. Yeah. So this is like going to be a bit wild. So my theory was, I was like, okay, so to incentivize myself to like probably teach you across the range of things in this week. I was like, maybe we'll end up continuing to do it like this because it might just be weird. But I was like, maybe I should just like choose like a random problem from the stuff covered by this week, and then just like do this problem, and then they'll likely be like, Jill, I don't even know what these words mean because you didn't teach me. And I'll be like, yeah. So let's use a random number generator to choose a random problem. 17 this week. Oh, is that what you said?
Yeah, what's that? Dinner, I think.
Should we leave it there, or do you want to
Let's see what
see
the
the
problem
problem?
is.
Great.
And if I reckon I can solve it in sub 5, then
Alrighty.
we'll do it.
Hello.
Mr. Angel!
I'm ready to study. I'm ready to work.
Oh, I was about to be like, look at all that.
Why you got what's on?
Losers.
We've proved so many things. Come
Let me just some things down
on.
before I make my road. Yeah.
Okay, so we've got a 9. Great, 9. Yeah, this definitely includes things, terms that I don't explain.
Yeah, that's nothing. Jalen, that's absolutely nothing.
Oh my god, I was like, it's fine if I just kind of skip the last bit of this. We didn't have
Why don't you
time.
just give me one from like earlier in the set of problems, right? Surely earlier in the problems will be.
Yeah. So this is a good one. I don't think you'll be able to prove this in this time, but I was actually going to give this to you.
What's risotto?
Oh, you've got rice.
No, is it curry? Do you want to have a little nibble of it?
No, I've had a big dinner.
I'm about to do a really cool thing.
Okay, I might do a really cool, have a shower. And
Oh, okay.
get ready for bed.
Showers are
Yeah,
pretty cool.
this is the last thing we're doing though.
Oh, no rush. Ooh.
I think you got a new card.
Yeah, it's a card for
Okay, which one?
So yeah, let's do this. Okay, this other one would take longer. Yeah.
Oh,
No.
it's a Medicare card.
Ooh,
Oh,
medically cared for.
medical care is pretty
Oh.
well, yeah, I feel like this is hard, but the other ones I was like to take away, you just like do them really quickly. So I'm like, maybe should I give you the one that's harder? And
No,
okay.
because the one that you think is harder will be impossible for me, whereas the one you think is easy will be hard for me.
Well, this is what I thought, but I'm like the things earlier, I was like, this is hard. You're just like, it's obviously this. So I'm like, no, let's try this one. Kind of graph of order 30.
What's that mean?
That has 30 vertices. Order. Have 3 vertices of degree 4 and the rest of degree 3. That's the first part.
Okay. Can a graph of order 30? No. Because that would be an uneven number of, it would be an odd number of odd vertices. As per previous proof.
Right?
Yeah.
What about if it's a multi-graph?
What about if it's a multi-graph? Still no, right? Because it's like that doesn't influence whether the vertices can be odd, whether there can be an odd number of odd vertices, because the fucking thing.
Handshaking theorem?
Which one's the handshaking theorem again? That's the like the handshaking theorem doesn't change depending on like which specific vertices, the edges are incident upon.
Yeah.
So it being a multi-graph does not change the problem.
Yeah, correct.
Hey!
See, I think I was right about how the even the harder was easier. Because I was
Yeah.
like, this is easier, and you got only 2 seconds.
But now I get the satisfaction of
Yeah.
ending on a
Yeah, exactly. Yeah.
thing. Yay! That's lesson number 1.
Lesson number 1.
So I think that Thursdays for the next couple of weeks will be good, but they will have to be digital as I'll be in Sydney. But that will be fun.